Hello everyone, and welcome to the TLE Eliminators PCD for Leetcode Weekly Contest 458. Hope you're all doing well. How was the contest, guys? How was the contest? I'm actually curious because I found the contest pretty simple this time, but I could see that the questions were a bit on the harder side. Like the second question is already graphs, right? What are your opinions on the contest? What questions did you find hard? Drop it in the chat. Anyways, before we start, I'd like to inform you. If you don't know already, TL Eliminators has self-paced courses which are out right now. The courses are divided into 4 different levels based on what stage you are at your learning journey. And as you can see, they're like pretty affordable, right? And there's even a sale going on right now. So do check them out. They consist of more than 40 hours of recorded lectures, more than 100 practice problems, hints and video solutions, as well as doubt support by high-rated coders such as myself, available almost 24/7, right? So do check them out. Okay, so third question and fourth question, yeah. Yeah, those were the interesting ones, I think. First one was very straightforward. I didn't attend the contest, but I'm registered. Will my rating drop? I am not 100% sure, but I think it does because it gives you that warning, right? If you don't want your rating to drop, unregister. So I think it will drop. Anyways. Okay, yeah, I guess first and second were easy for most people, so we'll go through that faster. Okay. All right. The first question was process string with special operations. Okay. And it's a very straightforward question, I think. You're given a string S and you're also given the characters star, hash, and percentage, right? So basically there's a string, it has either letters or it has the symbols star, hash, or percentage. If it's a letter, then append it to your answer. If it's a star, then remove the last character. If it's a hash, then make a duplicate of the string and append it to the same string. Otherwise, if it's a percentage, then reverse the current string, right? And I think this one almost everyone would have gotten because you just need to directly implement the statement because the length of the string only goes up to 20, correct? So the length of the string, so this is the main part here. Um, Length of the string in the input is only up to 20, right? So directly implement the statement in your whatever programming language of your choice. Um, Directly implement the statement, right? So I think this is just to test whether you know basic programming or not, right? So you can make a string, empty string, if it's a star, and if it's not empty, then you can remove the last character, right? So this is how you do it in C++. If it's a hash symbol, then you need to add itself to itself, basically append the same string, right? Append the same string to the back. And if it's a percentage, you can reverse the string, right? And this is how you reverse the string in C++. Otherwise, we can just add the character. If it's a normal character, we just add it to the end of the string and we return the final value. Okay. So I don't think we need to talk more about this, right? That's all for problem A. Yeah, you have not studied graphs, so you could do only one. That's understandable. Second question use graphs. Usually they don't, but I saw last contest also second question started using graphs. So maybe they're making it harder, or maybe they're just doing graphs nowadays. Anyways, yeah, Vikash, we will go through all the questions one by one. So don't ask for the third question right now. Yeah, so what is the time complexity? See, the which operation takes you the most? The duplication operation takes you the most, right? Because if you're duplicating a string of size 20, then the like duplication costs you 20 characters, like O of 20, right? And if you're duplicating a string of size 40, then it becomes size 80 string, right? So that's why the duplication is the most costly operation. And since the size of the string is at most 20, we can say that at most 20 duplications happen, right? So, so the time complexity will be roughly, this is a very loose bound, but the time complexity will be roughly n times 2 to the power n. I mean, this is a very loose bound, but it is enough for our purpose because this passes even for n equals 20, right? This passes even for n equals 20, right? Because it's the basic implementation of the statement, and s dot length is what I'm calling n over here, okay? So the length of the string is 20 at most. So if you assume that we add some characters, then we just do duplications. At most, it'll be n times 2 to the n, and that will still pass, okay? For the first question, alternate approach. Why would you want? I don't see why you would think of some alternate approach for the first question, because like it's literally just brute force the answer. I don't think there is exactly any alternate approach without making it very complicated. So I don't understand what you mean by alternate approach, Raghav. There is nothing to this question. You just need to read the question and just implement it directly. Okay. So if there are no more doubts, we'll move on to question B now. Okay. We're moving on to question B. Okay. Question B is a graph question. If you have some knowledge of graphs, specifically if you have knowledge of MST, okay, minimum spanning tree, if you have any idea about MST, then you will solve this very fast. Otherwise, I think it's almost impossible to solve. Like it's a very knowledge testing question. If you have the knowledge, you can solve it. Otherwise, you will not be able to solve it. Okay. So don't feel bad if you could not solve it. I think that just means you need to learn graphs. So you can check out maybe TLE level 3, where they go into graphs, I guess. Right? Um, yeah. So we have to minimize maximum component cost. You're given an undirected connected graph with n nodes. Okay. So it's a normal undirected connected graph with n nodes. And there are some edges. The edges are from node U to node V with weight of W. Correct? So from node U to node V with a weight of W. And those are the edges. We are allowed to remove any number of edges such that the resulting graph has at most k connected components. Okay. Let me just write problem B here. Okay. Problem B. We're given an undirected connected graph of n nodes. And we are allowed to remove any number of edges. Okay. So that's what the problem says. And the resulting graph has at most k connected components. Okay. So you must be careful what that means. Connected components. Okay. Right. And what do we want to do? We want, okay, so the cost of a component is maximum edge weight in that component. Return the minimum possible value of maximum cost among all components. Okay. Is there any other approach other than MST to this question? Uh, I mean, if you know union find, right, then you don't need to exactly know what MST is. It's either union find or MST. To understand this, like Kruskal's MST algorithm, I mean, they're very related, yeah. I don't think there is a way to easily do this without knowing union find, like DSU data structure. Uh, or even if there is a way, I think it will be pretty maybe complicated. At least I could not think of any way during the contest or right now to do it. But I guess you could, binary search. Let me think. Can you binary search this? Okay, yeah, obviously you can binary search the answer, yeah. So you could do binary search to find the answer for this question. So yeah, there's a way to do it without knowing union find, and I suppose that's binary search, right? Thank you for that, Arpit. Yeah, binary search can do it. But then with DSU, it's just maybe 5-10 lines to write the answer. That's why I use DSU. Okay, in the very end, I will explain a binary search and DFS answer, right? But for now, let's discuss the DSU answer. Okay, since I think that is like at some point, once you know DSU, and DSU is just some theory which you need to learn. And Solving with DSU just takes like five lines barely, right? Anyways, so yeah, you're given this and you need at most k connected components, right? Now we need the minimum possible cost, a minimum possible value of the maximum cost. Okay. Now what is maximum cost? Let us decipher this. Okay. Um, simplifying the question, right? Simplify the question. Simplify the question. And here maximum cost across all components. Okay. All components. What does this mean? Okay. And this simply means that is the max weight edge. Okay. Max weight edge. Fine. In the graph. Okay. So what does our question simplify to? It becomes remove edges from this graph, from this graph, while ensuring, while ensuring, remove edges from this graph, while ensuring that connected components, right? Connected components are less than or equal to k, right? Number of connected components is less than or equal to k. So that means we can't break up the graph too much, right? So the number of connected components should be less than or equal to k, and minimize the maximum weight edge. Okay, the maximum weight edge. And this is a simplification of the question, which I think is easier to understand what's going on. Okay, and why kth largest weight not works? Simple, because if even if you even you know what, Devansh, I'll answer your question after explaining the solution. Okay, yeah. So let's just continue and look through the actual solution, and then we'll come to your question. Okay. Remove edges from this graph while ensuring that no connected components, that number of connected components are less than or equal to k, and minimize the maximum weight edge. Okay. So the way we'll do this, the way we do these, and a lot of these questions where we need to minimize or maximize edge weights, right? On a graph, the way we do this is instead of removing nodes, we will add nodes. Okay. Sorry, removing edges, we'll add edges. So we're gonna do it this way: add edges to the graph. Okay, we're gonna do it in reverse. Add edges to the graph. Initially, there are no edges. Okay, initially, no edges. Okay, so if initially there are no edges, there will be exactly n connected components, right? And as we add edges to the graph, then slowly there will be slowly the number of connected components will increase until it becomes one. Okay, so one thing about this question, the input graph is connected. Okay, so if it's fully connected, that means the number of connected components is one for the input graph. Okay, so we will add edges to the graph. And what we're going to do is we're going to do an idea which is very similar to Kruskal's algorithm. Okay, so for this approach, prior knowledge should be either Kruskal's algorithm or DSU. So they're very related ideas. So I don't think there'll be many people who know Kruskal's and don't know DSU. Like that's not possible, right? But these are your prior knowledge for this approach. So what we're going to do is we're going to add edges to the graph, and we'll add the minimum weight edge each time. Okay, add min weight edge. Okay, why will we add the minimum weight edge? Because we're trying to minimize the maximum weight edge, right? We'll add the minimum weight edge if it uh, reduces the number of connected components, right? Reduces the number of connected components. This is the same thing we do for Kruskal's MST. Okay, number of connected components. But the way Kruskal's minimum spanning tree works is that it stops only when the number of connected components becomes one. Okay, but here we can stop when the number of connected components becomes less than or equal to k. Okay, so whenever it becomes exactly k, we can stop. So stop when uh, number of connected components Okay. Stop when number of connected components becomes less than or equal to k, right? And why does this work? It's using a greedy idea, very similar to Kruskal's algorithm, by taking the minimum edge weight each time, such that two connected components, such that the graph gets connected, right? Like two components get joined. We are basically finding the least cost to make the number of connected components less than or equal to k, right? So that's the idea for this question. Does that make sense? So this is basically the whole solution, I guess, to the problem. We add edges to the graph. Initially, we assume there are no edges. Add the minimum weight edge each time. If it reduces the number of connected components, stop when the number of connected components becomes less than or equal to k. So what will the idea for this look like? It will be something like this. We have a DSU, have a DSU data structure of n nodes. Sort your edges, sort your edges by weight, okay, by weight, ascending order, right? Ascending order. Then what we're going to do is pick minimum weight edge. And we're going to repeat this. So repeat until number of connected components or number of sets in DSU. Repeat until this is greater than k, right? Because we want it less than or equal to k. So pick min weight edge, pick minimum weight edge, join them. If why do we join them? We're joining them so that they can make a new connected component, right? So join them if it merges two sets, right? Merges two sets. Basically, we're taking two connected components and forming one connected component from that. And if we're joining, then we can do answer equals maximum of answer and the weight. Okay. And once this whole loop is done, we can simply return the answer. Okay. So this is the Kruskal or DSU approach to the problem. Okay. I will discuss the binary search approach after this. Okay. And now I can answer your question, Devansh. Why does the kth largest weight not work? So I'll show you an example. And let's say you have some nodes here, right? Okay. And there's an edge here, an edge here, an edge here, and this edge here. Okay. Now we have 1, 2, 3, 4, and our k equals 2. Okay. So we need at most two connected components. And we need the maximum weight edge to be the smallest possible. Okay. So in our DSU approach, we one by one add edges. So right now I'm going to assume that all the edges are removed. And when the edges are added, I will color them green. Okay. When I add the edges, I'll color them green. So first we find the smallest weight edge. Okay. So at first we'll just color all the connected components or the sets of the DSU. So these are all their separate sets in the start of the algorithm, right? Now we've picked the minimum weight edge. We pick the minimum weight edge, which is 1. And we can merge these two, right? We can merge these two into forming a new set, right? So we merge these two. Now again, we pick the minimum weight edge, right? And we merge these two. Now the thing is, the next minimum weight edge is here, right? The next minimum weight edge is 3, but we won't merge here, right? Because they're already part of the same set. This whole thing has already formed one single set, right? So we won't merge the kth one, and that's why we're going to end up merging this 4 and like these two nodes, right? And then we can stop and we can say our answer is 4. So our answer is not 3, but it's 4 because this third edge over here with weight 3, it's not doing anything, right? It's not merging to disconnected components. can't we make an MST and remove the edges from it? Can we do that? Yeah, we could make an MST and remove the edges from it. But then again, to make the MST, you already have to do the same process, right? Either you have to run crucicles or you have to run prims, right? So why not just while running crucicles itself find the answer? You can just stop ahead of time. So yeah, Akshit, you can make MST and you can remove the edges, I think. It's in fact the exact same thing. Here I'm just running crucicles. This is crucicles algorithm. To find the MST, you have to run it until this becomes 1, right? And then you're again removing the edges backwards. Instead, I'm not even adding those edges. I'm just stopping as soon as the number of sets becomes less than equal to k, okay? As soon as the number of connected components becomes less than equal to k, I'm just stopping it. What you're doing is you're going to do this and you're going to remove the last few edges again. So that doesn't make, like, that you can do, obviously you can do, but it's just going to waste some time. You can avoid DSU by using prims. That's true. If you do not know crucicles, and if you do not know DSU, you can use prims and avoid DSU. Yeah. So fine, go ahead. If you have prims memorized, then that will be fine. You're unable to send solution in chat. Yeah, I don't think you'll be able to send solutions in chat. It's fine. Put it in the YouTube comments if you want other people to see it, right? Anyways, binary search solution to this problem. That's also pretty simple. So for the prims approach, what's going to be the time complexity? Sorry, for the crucicles approach, what's going to be the time complexity? We have to sort all the edges, right? So to sort all the edges is going to cost you off number of edges, right? To create a DSU of n nodes is just big O of n. Now to unite two nodes, that is for a DSU, it's negligible time complexity. So we always assume that DSU operations are big O of 1, right? So the time complexity for this approach will be big O of m log m to sort all the edges plus n. Okay, so this is the approach with DSU. Right. Okay, what about the approach with binary search? Right, so this is approach 1. To use DSU, use a form of crucicles, except we stop when the number of components becomes less than equal to k. What about alternate solution with binary search, which someone suggested in chat? I forgot who suggested that. But yeah, alternate solution. If you do not know DSU and stuff, binary search. Okay. So the way we do it is, all you need to do is basically you need to binary search on the answer, right? So assume that maximum weight edge is X. Okay. Then all edges with weight less than or equal to X are a part of your, can be taken as your what do you say, can be taken in your current graph, I guess, in your graph, and remaining edges will be excluded. Okay, remaining edges can be excluded. Now if there are less than equal to k components, then this is a valid value of X. Okay, it's a valid value of X. So this can be your predicate function for the binary search, right? This will be your predicate function. And now you can do a binary search on X. Since you can show that it is monotonic, right? You can binary search on X. Binary search on X as it is monotonic, right? If your X is too small, then obviously you'll have too many connected components, so it'll become false. Then as soon as your X is big enough, it'll be true. So we just need to find the first value which makes this predicate function true. So that's why we can use a binary search approach. And what will be the time complexity? It will be big O of so to find the number of connected components, we need to do a DFS. So that's n plus m, and then the predicate function will be n plus m. That means, and the maximum weight, the maximum weight of an edge goes up to 10 power 6. So we can write it as max of weight I. So this is a binary search solution to the same problem. Okay. So this is the time complexity for the DSU solution, and this is the time complexity for the binary search solution. And I just wrote a brief explanation of how to binary search the answer. Okay. Although in contest, if you know DSU, I would prefer that approach. It's much more easy to think about and write. So here is just a template for DSU. Okay. If you do not know DSU, then study DSU and you can make your own template. So you can just copy paste it into problems. Okay. Now, what do? I sort the edges by weight. Okay. So we're going through the code now. I sort the edges by weight. My answer is set to 0 in the start. And this is my DSU. For each edge, so because they're sorted by weight, I'll be seeing smaller edges first. If the count isn't, so the way I have defined my DSU, count returns the number of sets. Okay, so count returns the number of sets. So if the number of sets has become k, that means I can stop because now there are only k connected components, right? So I can just stop. That's what I mean by once the number of connected components becomes less than or equal to k, right? So once it becomes less than or equal to k, we can stop, right? And otherwise, I will unite these two nodes, right? These two nodes of the edge, E of 0 and E of 1. And the way unite is implemented in DSU, if they are of the same set, it will return false. But if they are of different sets, it will unite it and return true, right? So if they were of the same set, I'm going to do my answer as maximum of answer and E of 2, right? This is the weight. So I'm going to take max of the answer and the weight. And then in the end, I'll return the answer. So if you see, this code is very similar to Kruskal's MST. Instead of max, we do a plus over here. And instead of stopping at k, we stop when all the edges have been united, right? So it's basically just Kruskal's MST code changed slightly. Okay, right. So this question does have many solutions. So other than this, you can do binary search, as some people pointed out, and some people also said you can find the MST by prims and then remove the maximum weight edges, right? So there are many ways to do it. Actually, no. Even if you find the MST by prims and remove the maximum weight edges, the MST just ensures that the sum of weights is less than or equal to, like, it ensures that the sum of weights is minimum, right? But it will not ensure that you took the smallest weight edge each time. So I'm not sure if your approach will work for prims. But yeah, DSU approach is very intuitive, I think. Yeah. Okay. Let's move on to the question C. If there are any doubts, please ask it now. Otherwise, we're moving on to third problem. All right. Okay. So this is related to the first problem itself. They have made it a slightly harder problem. You're given a string S consisting of lowercase English characters and the same special characters. Okay, the special characters are the star symbol, the hash symbol, and the percentage symbol. And you're also given an integer k. You need to build a string result, which is the same rules as before. If the letter is an English character, append it to result. If it's a star, then remove the last character of result if it exists. If it's a hash symbol, then duplicate the current result and append to itself. Okay. Yeah, I guess prim should work, but I'm not 100% sure about it. Because the way prims works is it it does like a modified Dijkstra basically, right? So yeah, it also, yeah, okay, yeah, prim should work. Yeah. Makes sense. Okay. And then again, as before, the star symbol, it will remove the last character. The hash symbol duplicates the string and appends it to itself. And the percentage symbol reverses the current string. Okay. Now, what is our task here? The task is return the kth character of the final result. If k is out of bounds of result, return dot. Okay. And what do they mean here? And why have they asked it like this? So the idea is that the string goes up to size 10 to the power 5. Okay, the string goes up to size 10 to the power 5. So it is infeasible to actually do this process ourselves, right? Last time the string size was only up to 20, but now the string goes up to 10 to the power 5. So it is infeasible to think of doing this, like actually storing the string, right? Because it says that the length of the string will not exceed 10 to the power 15, but obviously we cannot store a string of size 10 to the power 15 in our RAM. That makes sense, right? Yeah, so basically the idea is that we cannot actually store the string, but we need to somehow find the kth character where so it's similar to problem one, but we just need to find the kth character without actually storing the string. Okay. And if k is out of bounds, we need to return a dot. Q1 except s dot length, which I will call n by the way, goes up to 10 power 5, 10 power 5, and length of result, right? Final length of result. Result is the resultant string after all the operations are done. That goes up to 10 power 15. And we need to find the kth character. Okay. Okay. So now the first thing we can do, right? When you read this problem, it might be a bit confusing, but the first thing you can do is you can think about. So this is, I guess, what can you call it? You can call it maybe intuition, but it's not exactly intuition. You're just thinking about what to find, right? So what is the final length of the string? Okay. What is the final length of the string? Okay, and we'll call this n. Fine, we'll call this n. The current length of the string we'll call as n. And we can find this without actually making the string itself, right? So every time a new character is added, every time, so initially n will be set to 0, and every time a new character is added, we will, every time a new character is added, we can do n plus plus, correct? We can do n plus plus. Otherwise, if there is a star, right, we can do one character was removed. So we can do n minus minus if n is greater than 0, and if there's a hash, that means the string got doubled, right? We duplicated the string and appended to the end. So it'll simply become n becomes twice, right? And then if we have a percentage symbol, nothing changes because um, the value of n remains the same even if you reverse the string. So this much I think should be obvious that we can calculate what the final length of the string will be. Okay, right? So when you look at this, does this make sense? What is the final length of the string? And we'll call that n. Initially, n will be 0 at the start. Every time a new character is added, we can say that n has increased, right? We can say that n has increased. So we do n plus plus. If we have a star symbol, that means n minus minus if n is greater than 0. If we have a hash symbol, we can double the n. If we have a percentage symbol, the value of n does not change. Okay. And we can say, I'll show you the code for this. This is the code. Okay. So we define n equals 0. Note that we should use long type because the size of the string can go up to 10 to the power 15 they said, right? If it's a star, n equals, so the way I've written it is max of 0 and n minus 1. So that way it will never become smaller than 0. right? If n is hash, n gets doubled. If n is percentage, just do a continue. Otherwise, it's a normal English character and we do n plus plus. Okay? And if now we can check whether k is in bounds or not. Okay? Now we can check whether k is in bounds or not. Right? Now we can check if k is in bounds or not. Right? So when is k in bounds? So k has to be less than or equal to n. Right? K has to be less than n. Right? So in this case only it is in bounds. So if it's out of bounds, we can simply return the dot symbol, right? So it will be out of bounds if n is less than or equal to k. So opposite of this thing, if not k less than n, or in other words, if n is less than equal to k, we can simply return dot. Okay, so we know that the final string length is n, and we need to find the kth character. So that means k should be less than n, right? Because k is zero indexed. So if it's out of bounds, we can simply return dot here, and we have solved at least one part of the problem. Okay, Karan, if you have a doubt in question two, now you'll have to ask it at the end of the session. Okay. Yeah, because we've already moved to question three and we should work on this now. Okay, right. But now we have only found the size of the string. Okay. Now we still need to find the kth character. Okay. We need to still find the kth character. We have just found the size of the final string and we have found if it's valid or not. Now, now assume k is less than n equals final length of the string. Okay, of the string. Fine. We need to find the kth character. We need to find the kth character. Okay. So what we are going to do is, let's use our second intuition, is that try to keep track of position of k in reverse. Okay. Position of k while doing the operations, while doing the operations in reverse. Okay. What do I mean by this? So for example, let's take an example. So we have an example here. Let's say our string was AA, and then I think star means to double, right? So let's say we have the string AAB, then star, then star. Okay. And we had to find maybe the seventh character. Okay, we had to find the seventh character. So k equals 7. Okay. So then if you see the string, it is going to become AAB, AAB, AAB. Right. So this is going to be the final string, right? Like once you double it and then again you double it and it becomes something like this. Maybe let's make it more complicated and let's have a percentage. Sorry, we have a hash symbol at the end. Okay, wait, star means remove the last one. Okay, so there should be two hashes then. Hashes and one star. Okay. So this means now you double it, and this means remove the last character. Okay. So the final string looks like this. And the value of n will be simply the count of this string, right? So it will be 3 into 2 minus 1. So that's 6, 12 minus 1, n is 11. Okay. And we need to find the seventh character. So this is the 0 because k is given as 0 index. Okay. So this is 0, 1, 2, 3, 4, 5, 6, 7, right? Basically, we need to find a. Okay. So now basically, let's say this is the seventh character, right? And we have a pointer on it, right? Right? 0, 1, 2, 3, 4, 5, 6, 7, right? And now we have a pointer on it. Imagine we had like a pointer on this, okay? Now, when we do the operations in reverse, we can keep track of what happened. Okay. So let's imagine we're keeping this pointer and we're trying to see how the operations go in reverse. Okay. So if we do this in reverse, we see that some character was deleted at the end because there's a star symbol. That means some character was deleted at the end from this step to this step. So we can just add a question mark at the end and we can be like, okay, there was some character which was deleted. I don't know what, but this was the size of the string. Okay. So n becomes 12 over here. And this is, we're trying to basically undo the step of star. Okay. So that's the idea over here. Now the next thing is the hash. Okay. The next thing is hash. And we're going to see what happens when we try to undo the hash. Okay. So when we undo the hash, basically the string becomes something like this, right? So this had doubled and it had formed this. Now the pointer which was here, right? So when you're undoing a hash and the pointer which was here, you can say that since this half and this half, they are duplicates, right? This half and this half are duplicates. So this value should be the same as whatever value was here. Okay, whatever value was here, this value and this value will be the same value. Does that make sense? We are keeping a track of k from reverse. Right? We're keeping a track of where this kth character has come from in reverse. Okay. Now what do we do next? What we can do next is we see the next character and the next character is another hash. So that means there was another doubling, right? There was another doubling and our string was something like AAB, right? And here, because this was on the left half, not the right half, so nothing changes and K remains this, okay? So here n equals 11, K equals 7, n equals 12, K equals 7 still. Then here n becomes 6, K becomes 2, here n becomes 3 and K remains not 2, 1, sorry, because one indexed, right? So 1, okay? Now, what is the previous one? In the previous one, we simply added a character B to the end. So that means if you want to think in reverse, that means one character was removed from the end, right? One character was removed from the end, and that was the B character, okay? So now our size of n will be 2, right? And our k will still be 1. Now again, one character was removed from the end at A, right? We have an A over here. We're going through this in reverse, right? So we went here, 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 and we reached here. Now we're removing some character, and in the idea is we're removing the same character, which is the one we tried to find, right? So our k equals 1, and we're removing character at position 1, right? We're removing character at position 1 when we're doing this in reverse. So that means that at this point, that character was added, right? At this point, that character was added. So we can say answer is A. A is the character at 7th position of the result string, of the result string. Okay. So this is the broad intuition for what we're going to do. We are basically going to keep track of the position K while reversing the operations. Okay. While doing the operations in reverse, we're going to keep track of the position of K. Okay. So what is our idea? First, find n, which is the length of string result. Right? This is the length of the resultant string. Then, if not K less than n, return dot, right? Because then there is no possible value. Otherwise, keep track of n and k while doing the operations in reverse or undoing the operations while undoing the operations in reverse order. Okay. in reverse order. And then when we're doing the operations in reverse order, when kth character is removed from the string, then we have found our answer. Okay. Then we found our answer. We found our answer. So whichever character removed it, that character will be the answer. Okay. And let me just make more sense of this. So how to do in reverse? Okay. How to do these operations in reverse? How to do operations in reverse? Okay. So basically you have your string which has some characters and some operations, right? So like hash percentage star hash percentage hash star, something like this, right? So whenever you see a star, what does that mean? Star simply means that something was deleted, right? Star means delete something. So what happens is basically we can say that what is the effect on n and k? So star in reverse, what is the effect on k? N increases by 1 and k is unchanged. Okay, that's the effect of n and k using the star symbol in reverse. Okay, now what about the percentage symbol? Well, percentage simply means reverse the string, right? So n is not changed, but k becomes reversed. So k will become the value at the reverse position, which is n minus k minus 1. Okay, what about the hash symbol? In the hash symbol, n becomes half, right? Because if you saw hash symbol, then to undo it, it means that before n was half the size. So we can divide n by 2, and we can say that what happens to the value of k if k was greater than n by 2, greater than equal to n by 2, then we can say that k is sub, you can do this, and you can otherwise else k is not changed. Okay, so if k was already in the first half, k will not change, but if k was in the second half, then we can say that k is same as the value which is k minus n by 2. Okay, because when we're duplicating a string and this was k value, then this string, the value over here also, which is k minus n by 2, that will be the same value. Okay, that's why when we undo the operation, we can say that k equals k minus n by 2. Okay, and if it's a character or alphabet, right? If it's an alphabet, then what's the effect on n and k? Okay, we can say that n minus minus k is unchanged, right? But but if n was equal to k, right? So that means that the character which we're looking for, that one was only removed. So after doing this, if n is equal to k, return the alphabet because that is the answer, that is the alphabet which we were looking for. Okay. So this is basically the idea. We do the operations in reverse and we keep track of the size of the string at this point, and we keep track of k. K means some index of the value which we're searching for. Okay. Does that make sense? So let me show you in an example. Let's just take the example from one more example. Let's say CD percentage hash star percentage. Okay. So let's do the whole process with an example. Example. Okay. And it's CD percentage hash star percentage. Okay. So let's find out first n, which is the length of the final string. So when we see C, so initially n equals 0. Okay. In the start, n equals 0. Uh, and then when you see the first character, n becomes plus plus, so n becomes 1. Then when you see the second character, again n becomes plus plus, so n becomes 2. Now when you do percentage, it means that it will reverse the order of the characters, right? So the size of n does not change. So n still remains 2. Now when you're here, um, when you see the hash symbol, it means double, so n becomes 4. When you see the star symbol, it means -1. So n becomes 3. And then when you see the hash symbol again, it's n becomes doubled. So n equals 6. Okay. So length of result, we can already say length of result will be 6. Okay. And what is the k we need to find? K we need to find is 3. So we need to find the third character. Okay. Find the third character. Find third character. Now we see that 3 is less than 6. So that's a valid position to find, right? 3 is less than 6, and we can find the third character. Okay. Is in zero indexed, obviously, find the third character. So now we do the whole operation in reverse. We have n equals 6, and we're going to go backwards in this string, and we're going to figure out where that character came from. Okay. So we have k equals 3, n equals 6. Okay. And this is at the very end. Okay. So this is at very end. Now, when we see the first hash, remember what hash means? Hash means that it's a doubling. So now when we do it in reverse, we need to do a halving, right? So n becomes 3, it becomes half. And since k is exactly like this, so if there were 6 characters, k would mean this character, right? So now when we do the halving, it means that k was the same value as this character. So we can say that k is 0 now, because k is subtracted by 3, right? It was in the second half and we subtracted by 3, we found a same value in the first half. Okay. Now what? Now we have a star. So star means something was deleted. So we get k equals 0, n equals 4. We don't really care what was deleted, but something was deleted. So we can say that the size is increased again. Now while doing in reverse, we get another hash. So that means k equals 0 and n equals 2. Now since k was already in the first half, we don't need to do anything to k, only n gets halved, right? Now we have a percentage. That means the value was reversed. The positions are reversed. So n will not change, n will still remain 2, but k will become 1. Why? Because that's 2 minus 0 minus 1, right? So basically, if this was k, but if you did a reverse operation, then now this will be k, right? So it will get reflected along the midpoint, right? If this was k, then now this will be k, something like that. Okay. Now in the fifth operation, we see that the next character is a d, right? And we're removing a d. Removing d, like that's what the operation happens. And basically, k is 1 and n becomes 1, right? So we saw that we removed the character which we want. Removed character at first position, right? And that means that this character which we were searching for all along, it was a D. So we can say that answer is D, and we can return D. Okay. So that's what I mean by doing this in reverse and keeping track of n and k, right? And again, you can go through the operations. With a star, n becomes plus plus. With a percentage, n is not changed, but k becomes mirrored. With a hash, n gets divided by 2. And if it's an alphabet, it's n minus minus. Otherwise, if we're removing the alphabet which we're searching for, then we found our answer and we can print it. Okay. Does that make sense, guys? You're confused during the contest? That's okay. I get it. Like, if this is the first time you're seeing a question like this, yeah, it might be a bit confusing. Let's have a look at the code. That should clarify things. Okay. So here we're simply finding the value of n. I already explained how we do that. Now we reverse the string s. Okay. So this is so that we can process the operations in reverse. If it's a star operation, n just increases. If it's a hash operation, n gets divided by 2. And if k is greater than or equal to n by 2, so now this is n by 2. So if k is greater than n by 2, we subtract that. If it's a percentage operation, nothing happens to n, but k becomes flipped, right? K becomes n minus k minus 1. Otherwise, um, we subtract n with 1. If n has become less than or equal to k, actually, if n has become equal to k, we can return the current character itself, right? Here I just put a return dot. This will never run. This return dot will never run. But since this is a function which should return something, I put a return dot at the end. Okay. What is the time complexity of this? There is no sorting, there is nothing. We're just going through the string once, then reversing the string and going through the string again, right? So the answer is basically size of the string. So the time complexity is simply big O of n. Time complexity of the solution is big O of n. Okay. Any doubts on this question? Any doubts on C? I solved the first question only. Please suggest what should I do. I think if you solve the first question only, that means that second question was a very direct graph knowledge question, right? So I think you should practice graphs because I think even if you have like some basic amount of graph and binary search, either graph or binary search, so you should practice those. Does that make sense? A victory. Okay. Guys, any doubts in C, please ask. Any specific doubts with the approach I explained? Otherwise, we will move on to D. Okay. Okay, I'm not getting any doubts on C, so I'll move on to the next question. Fine. Okay. And for Mini, if you're confused during the contest, right? See, that's how it is. These problems are challenging, right? You need to give them time. You need to do more practice outside of the contest as well, right? And if this is your first time seeing the problem, I think it will be pretty helpful to implement this yourself because this kind of idea of keeping track under some operations is a common idea, okay? Fine, problem D. Longest palindromic path in graph. So I'll just go drink some water and then we can start this question. Just a minute. Okay, let's get started on D. You're given an integer n. Again, we have a graph. So you and an undirected graph of n nodes and a bunch of edges. There are no weight on these edges. Okay. You're given a string label of length n, where label of I is the character associated with node I. Okay. So the nodes are labeled. That means there are some character for each node. Like if you see node 0 has character A, node 1 has character B, node 2 has character A, and so on, right? Now you may start at any node and move to any adjacent node. Visit each node at most once. Return the maximum possible length of a palindrome that can be formed by visiting a set of unique nodes along a valid path. Okay, so the question is very simple. We basically need to find a path on these nodes such that we get a palindrome. Okay, so let's take this example graph where they've given us four nodes. You can see that it's A, B, C, B, right? So here the longest palindrome is clearly B, C, B, right? Does that make sense? So the question is straightforward. Right? This is the question. So it's a very straightforward question, but I guess implementing it would be not that easy. Uh, okay, n goes up to 14, fine. And this is a very interesting thing. The n is not like 10 to the power 5 or 10 to the power 3 or something like that, as they're usually in questions. N goes only up to 14, right? And that should already give you an idea that it's going to be some kind of brute force or maybe DP bit mask idea. Okay. Please also tell when you saw the problem. So you're talking about D. Okay, fine. I'll do tell you what intuition comes to my mind when I saw D. Okay. So N goes up to 14, and the number of edges, it can go up to N minus 1. So it's at least a tree and at most a fully connected graph, right? It goes to N times N minus 1 by 2. And N minus 1 means it's connected. So the number of edges means basically it's going to be somewhere between a tree to a fully connected graph. Okay. So that's the idea. Edges are N minus 1, number of edges. Okay. So that's how it is. So let me tell you what I first thought when I saw it. Okay. So when I first thought, my idea was, what if we try to do all the possible combinations, right? If we try to do all the possible combinations either with next permutation, right? A path can be basically a series of nodes, right? So we can try all possible combinations using next permutation. That will be n factorial, right? So brute force ideas will be n factorial. Brute force, it will be n factorial, right? And 14 factorial is roughly 10 to the power 10. So it will time limit exceed. Okay. Now, similarly, if you do a backtracking idea, right? Even if you do a backtracking idea, in the very worst case, in the very worst case, you can have a complete graph of 14 nodes, okay? And all the values are A. Let's say all the labels are A, okay? And if you have a complete graph of 14 nodes, all the labels are A, what happens? You will have to visit each permutation anyways, right? So if you have a complete graph, so I'm just drawing a complete graph of like size 5, right? So the total number of paths in this will be n factorial, and basically any path is a permutation, right? If you take this path, it's a permutation. This path is a permutation. So all the paths in this complete graph will be a permutation. So will be a, sorry, not a permutation, a palindrome, right? Any path in this graph will be a palindrome. So that also, even if you do with backtracking, it will be n factorial itself. Okay. So that's why if you do a backtracking approach, DFS backtracking, it will be too much. Make sense? Because Manav, your backtracking idea is not going to be 14 times 14 plus 100. It's going to be 14 factorial. Okay. Total number of paths in a graph, if it's a complete graph, is n factorial. So that's why it's going to be 14 factorial. Okay. And 14 factorial is very large. Is 10 to the power 10. Okay. So now the ideas you need over here. Okay. And then after this, I'll tell you what my intuition was. My intuition was, look, it's n is small, right? So maybe there is some bit mask way to do it. Okay. So that was my intuition because I've seen problems like this before. So that's what I thought about. So some knowledge you'll need, some knowledge needed will be bitmask DP. Okay. I mean, obviously you can come up with this yourself, but I think that is very less chance to do that in contest time. But you need roughly bitmask DP ideas. Okay. You need some idea of how to do bitmask DP. Okay. If you want to learn bitmask DP, obviously you can Google it or you can check out level 4 TLE course. It has DP and I think it does go into bitmask DP as well. Okay. Okay. So now here is the idea. So I'm not sure exactly how to give an intuition for this because once you think about bitmask DP, you kind of get the idea itself. But let's try to go through an intuition. Okay. Let let dp of mask I to j. Okay, okay, equals 0 or 1, true or false. And what does this mean? It means that starting at node I and ending at node j, visiting all nodes, visiting all nodes in mask. What is a mask? Mask is basically a bit mask where 0 means it's visited and 1 means it's unvisited, right? So it'll be some kind of binary string like this. So all the positions which are 1, so the 0th node will be visited, the first node is not visited, and so on, right? First node is not visited, 0th node is visited. That's what a bit mask means. And so this will be our DP state. Okay. And if you ask me where I got the intuition from, it's because n was small, and when n is small, usually bitmask DP works. And basically, the way palindromes work is like when you have a palindrome of a smaller size, you can make a palindrome of a larger size, right? So from that, I had the idea that maybe we can compute smaller palindromes, and based on that, we can compute larger palindromes. And that's why I thought about bitmask DP. So let me explain the bitmask DP solution, and then I'll come back to some more intuition for why this works. Okay. So let DP of mask of ij equals 0 or 1 based on starting at node I, ending at node j, and visiting all the nodes in the mask. Is it a palindrome or not? Okay. Is it a palindrome or not? Okay. So this is the idea. This is the DP we're going to run, and I'm going to show you that transitions on this DP will work for a problem. Okay. So now the idea is, let's say that starting at some node I, going through some bunch of nodes. Okay. So these nodes are unknown nodes. We don't care about them. And ending at some node j, this is a valid palindrome. Okay. Assume that this is a valid palindrome. Valid palindrome. Okay. Now, if we can somehow check the adjacent nodes in this, check the adjacent nodes to I and j. Okay, if we can find the adjacent nodes to I and j such that this and this has the same label. Okay, so some adjacent nodes have the same label, and this node has the same label. Then what will this mean? This will mean that this whole thing is already a palindrome, right? Now we add two nodes at the end. That means that those two nodes will just form a palindrome starting at this node A, ending at this node B. So basically, using the fact that DP of ij and this bit mask was true, we can find that DP of mask and these two new nodes will be added, right? So the two new nodes will be added to the mask, and we start at A to B. We start at A, go to B. That this is also a valid path with the palindrome. Okay. I hope that makes some sense. Basically, what I'm saying is, if we know that from I to J there is some path with a palindrome, then from A to B there's also a path which is a palindrome because A is adjacent to I, B is adjacent to J, and the label of A is equal to label of B. Okay, does that make sense? Humble request to discuss the at coder contest. Okay, I will put forward that suggestion to the higher ups at TLE. Okay, all right. So what from this what can we get? We can get that basically B as we defined, B represent is their path visiting all the nodes in the mask starting at I. And if you're not following this right, you definitely need to learn bitmask DP, I think, because without that, it's very hard to explain it. Ending at J. which is palindrome. Okay. Okay, so this is what the DP represents. And the way the DP will transition is we can find the answer for larger masks from smaller masks, right? So if you have some nodes visited, then some path which visits a new node, right? If we have the answer for DP of, if we have calculated, if we have calculated DP of mask of ij for all masks less than m, right? Then we can simply calculate DP of mij as well. DP of mij as well. And what we can do is basically say that since we have already calculated those, we just need to so every ij which so actually we're going to calculate it bottom up, right? So that's why this transition is not very easy to write. But basically, if we have already calculated a path, we can extend it by finding two adjacent values which are equal, right? So when we are calculating the smaller masks itself, when we're calculating all the masks less than m, then if any of those masks could have been extended to inj, right? If they could have been extended to inj, then that's why dp of mij would already be set to 1. Otherwise, it would be set to 0, right? And if it is set to 1, we can try find more adjacent nodes and extend this dp even further. Okay, so I think this will be much more clear once we get to the code. But let me just show you that this state is representable. If 14 factorial is 10 to the power 10, we can show that 2 to the power 14 times 14 times 14, since the start and end can be any of the 14 nodes, and 2 to the power 14 is the bit mask. This is about 10 to the power 6 or 10 power 6, right? So this is very easily representable to have a DP like this. Okay. So I think I should explain this a bit more clearly. Let me just find how to phrase this properly. Um, Given a value of DP mask ij equal to 1, find all A which is adjacent to I, find all B which is adjacent to J, such that A and B are already not in our path, right? A and B cannot be in our path, so they cannot be in mask. They're not in our mask. Label at A is equal to label at B, right? Label at A equals to label at B. Then we can say that DP of mask. So this new mask, right? Where A and B are also included in the path, starting at A and B, that will be set to 1. Okay, so this is basically our DP transition. Okay, DP transition. And how does this work? It works because we'll do from increasing value of mask. So we'll do from mask equals to 1 all the way to mask equal to 1 left shifted by n. Okay, so I guess you need to know bitmask for this. I'm sorry if you don't know bitmask and you're not able to understand this. But basically what I'm saying is if there's a given path from which starts at I and ends at j, and it has some given bit mask, then we can extend this mask. We can add two nodes to the left and right, right? We can add two nodes to the left and right of the path, some path over here, and these are the two nodes we added. And if those two nodes are equal, then we can say that this is also a valid palindrome, so we can set it to 1. And because we do it in increasing value of mask, this will set all the values of valid paths to 1. Okay, does that make sense? We do this in increasing order of mask. Okay. Now, what will be our base case for the DP? Base case for the DP. So when you have single nodes, right? When you have single nodes, that's a valid palindrome, right? If you just have one node, which is like label A, then obviously there's a palindrome of length one. So our answer will be at minimum one, right? So even if we have single nodes, let's say like this, right? And this is our graph, then answer will be at minimum one because we can just take this string. So one of our base cases can simply be dp of, so the mask will be I, start at I, end at I. So the path starts at I, ends at I, and the only node we have visited is I, and that will always be one. Okay. And for even length palindromes, we also need a base case. So two nodes. So all the nodes which are connected by an edge and they have the same label. Okay. So those nodes will be our second base case. These are so that we can have both even and odd length palindromes. Okay. Ij equals 1 if edge between I and j and the label of I equals to label of j. Okay. So this is our base case for our DP. And basically what I'm saying here is if I have two edges like this, if I have two nodes like this which are connected by an edge and they have the same label AA, right? So that means if I take these two nodes as my path, then I can say that I have a palindrome of length 2, right? So the nodes visited in the path are this one and this one. So add those two nodes to my bit mask. I can say this is my starting and this is my ending. Or in reverse, this is my starting and this is my ending. So both of those will be turned on in my DP. Okay. And using this as a base case, we can build our whole DP, right? And basically the way our DP works is it finds a valid state. Then for every valid state, it tries to extend that valid state by finding stuff adjacent to A and finding stuff adjacent to B, which can extend our palindrome. Okay. So this is the transition. This is our transition. This is our base case. And what's our answer? Well, we need to find the maximum length path, which is a palindrome, right? So we need to find maximum pop count or maximum number of set bits of a mask such that dp of mask ij is 1. Okay, so it can be any I and any j, starting and ending does not matter. But as long as it's 1 and the given mask is on, like if and the given dp is 1, that means it's possible. Then we find the maximum pop count of that, and that will be our answer. Okay. So it's a standard-ish bitmask DP idea, somewhat standard bitmask DP idea. Bitmask DP. And what's the memory complexity? So since we are forming this DP array of mask ij size, right? The memory complexity will be big O of 2 to the n times n times n. And we saw that that's roughly 10 to the power 6. So that fits in the memory complexity. And what's the time complexity? That will be big O of 2 to the n times n squared times, since from each node we're trying to find adjacent nodes, right? So it will be roughly how much adjacent nodes we are trying to find. So in the worst case, that's another n squared. So in the worst case, the time complexity is big O of 2 to the n times 14 to the power 4, which is a bit high. But as you can see, it's still 10 to the power 8. So it'll still pass. Like it'll barely pass, but it does pass, right? This is the memory complexity and this is the time complexity for this bitmask approach. Let's have a quick look at the code for this. And then maybe I'll show an example also of how this works, so that's understandable. First, we simply find an adjacency list. Then we define our bitmask DP array which is of size 2 to the power n, which is the maximum size of our bit mask, right? So bit mask is basically like ones and zeros, such that the positions which are turned on, that means we have visited this node, right? If it's a one, it means we have visited this node in the path, and if it's a zero, it means that we have not visited this node. Okay, this node. So that's what our bit mask is. And since there are at most 14 nodes, 2 to the power 14, or 1 left shifted by n, that is how much size we need for our mask portion of our DP. Then this is I and j, which means the starting and ending point, and that becomes size n each. Okay, and then I set all of this to 0 in the start. Now here we're going to handle our base cases. So for all I, like all paths from I to I itself, right? All paths from I to I itself, single node base case, and those are palindromes, obviously, because there's only one character, so it's a palindrome. So one left shifted by I, so only one node is visited, and that's one left shifted by I, and it starts at I, it ends at I, and that's why I set it to true. So basically, this means that starting at I, ending at I, and the nodes visited are I itself, that forms a palindrome. Okay. Now I go through all the nodes. I find adjacent nodes such that the label is same, and I say that a path starting at I, ending at j, and visiting these nodes in between, that is set to 1. Okay. Now that I have done that, I can go through all the values of my bitmask DP, starting from mask equals 1 all the way till mask less than 1 left shifted by n. So I'm visiting all the masks in increasing order. I choose my I and j. Okay. I choose my I and j such that we have not already, such that they are part of the mask, right? So if it's not in the mask, I can't choose an I and j. And then what I do is I take my answer as the max of the value of the built-in port count of mask. So basically what I'm saying is if this DP value is valid, right? If this DP value is not valid, I'm just continuing. If this DP value is valid, then take the maximum for built-in port count of that. So that's the number of ones which are set in the mask, right? So we're taking the number of ones which are set in the mask such that DP of mask of I and j is 1. Okay. And once we have done this, so the way we do our transition is given a value such that DP of mask I and j is 1, we find all A which are adjacent to I, all B adjacent to J, such that they are not in the mask and they have the same label, right? So that's what I'm doing here. Here A I've written as II and B I've written as JJ, right? So if they're in the mask, I just continue it. So I want II and JJ to not be in the mask. That's why these two lines. So I find stuff which is not already in the mask, and they cannot be equal also. II should be different from JJ, right? And I basically see that the labels are equal or not, right? If their labels are equal and they're not in the mask, then I can extend the mask by adding these two nodes. And I can say that starting at II, ending at JJ, there's a valid path, which is a palindrome. So I set that to 1. Fine. Then finally, I print the answer, which is simply the max value of pop count, such that the DP was 1. With this constraint, it should TLE. Yeah, so the reason it is not TLEing is because 10 to the power, like 6 times 10 power 8 can barely pass. But the reason is actually, like this n squared is like an overestimate slightly, right? This n squared is a slight overestimate. We are only visiting valid adjacent nodes, right? We're only visiting valid adjacent nodes. So you could write this as maybe like sigma squared. So this is the number of valid adjacent nodes. In the worst case, it becomes n nodes. But the thing is, in practice, you won't actually visit that much, and it'll become roughly 10 to the power 8 operations itself, right? Because here I'm visiting stuff which is adjacent to I and stuff which is adjacent to J, which is already not set in the mask. So in practice, it will be around maybe 10 to power 8. So in practice, it will be roughly 10 power 8 operations because it's not actually it's not actually this much. It's something like, I think the technical way to write it is something like this, right? And this is the number of nodes adjacent. Adjacent to a given state. And if it's not even valid, so we just skip them, right? So this is the number of nodes adjacent to a given state which are valid. And even in a complete graph, that won't be that many states. Why can't we do with a BFS and deck? What do you mean exactly? Like, can you explain your approach more? The reason we are not doing a BFS or DFS is that it will become like backtracking mostly and it will become 14 factorial. But I don't understand what do you mean by BFS and deck. Can you try and explain that? If you do a backtracking, right, uh, with a BFS or DFS, you'll end up visiting all possible paths. So that will be 14 factorial, which is too much for the constraints, right? That's why we're using a bitmask DP approach. And where did I get the intuition for bitmask DP? Well, because the constraints were low and the fact that you can extend a palindrome and you don't need to know which exact nodes were there in the palindrome, right? We can extend palindromes. So I guess this is the core intuition. Core intuition. We can extend palindromes by adding a node in the end and a node in the start, a node in the start, a node in the start, and a node in the end. As long as, as long as we know that the nodes in the middle already form a palindrome. As long as we know the nodes in the middle are already a palindrome, are already a palindrome. And obviously the two nodes we add in the end, they should have equal labels, right? A node in the start and a node in the end, they should have the equal labels. Then only we can extend it, right? Same label, obviously, right? Then only we can extend. So basically, we don't need to know exactly which nodes are forming the palindrome or what the exact path is. As long as we know starting at I and ending at J, there is some path which is a palindrome, then we can extend it by taking something adjacent here, with the same label, right? Label of J equals to label of I, basically. Um, so as long as label of A equals to label of B, we can extend this path. And similarly, we can keep extending the path. And that's why we're using a bitmask approach. So we're just keeping track of which nodes we have visited and where we started and ended. And that is the only thing important for the question. And that's why we have a bitmask DP approach to it. Okay, does that make sense? Any doubts, please ask. I'm sure that if this is your first time with bitmask DP, that explanation would have been very confusing. But if you have done maybe 3, 4 problems, I think that explanation would have explained everything to you on how to solve that problem. Okay, guys, now you can ask any general questions or general doubts which you may have. Anything on your mind? Someone said they had a question on problem 2, so you can ask that now if you're still here. Any general questions regarding CP or you would practice? Any questions regarding D or C problem or B problem? A. How should you ideally upsolve? Okay, so the way we do this, right, is basically the way I recommend it is you do the contest. Okay, do the contest. Then after that, you end up like either you run out of time, right? You can still solve and you run out of time. In which case, keep solving, or maybe next day after the contest, solve the questions which you couldn't because of time. Solve the questions you couldn't because of time, right? Or otherwise you got stuck at some point, right? You got stuck at a question completely and you could not make any progress. So solve one question which you were completely stuck at. Okay. Solve one question which you were completely stuck at. Okay. So basically, if you couldn't solve because of time, you should just keep continuing solving until you get stuck. And then once you get stuck, you should solve one question which you were stuck at. Okay. Some people might solve two also, that's also fine. But usually if you solve at least one, that's more than good enough to progress, right? Um, yeah, that's basically it. Can you explain why backtracking approach is n factorial? Okay. for problem D, I suppose. So I'll just give you an example graph, okay? Backtracking and why it is n factorial, okay? And I'll give you an example graph and I'll ask you how many paths are there on that, which are a palindrome, okay? And you should understand that from seeing it itself, okay? Let's say I have a graph of 5 nodes, okay? Which is like this. Um, okay. I have a graph with 5 nodes, which is completely connected, okay? Completely connected. And all the labels are A, okay? All the labels are A everywhere, fine? All the labels are A in all the nodes, okay? Now here, no matter what you path you pick, no matter what path you pick, no matter what path you pick, it's always going to be a palindrome, right? Is that clear, Anirudh? No matter what path you pick, it will always be a palindrome, right? Right. Even if you start at 3 and if you go to 2, then you go to 4, right? This is a valid path and the string will be AAA and that's a palindrome. Since all the letters are equal in the string, any path in this graph is a palindrome, right? And now when you do a backtracking approach, it's going to check all the paths, right? Backtracking will end up checking all the paths anyways on this graph. Will check all paths. Will check all paths, right? So basically the answer becomes the amount of time backtracking is going to take is big O of number of paths in a complete graph in the worst case. Okay. In the worst case, backtracking will take big O of number of paths in a complete graph. Fine. And how much is this? You can see that number of paths in a complete graph is n factorial. And why is it n factorial? Because you can visit any node in any order, right? You can visit node 5, then you can go to 4, 3, 2, 1, or you can go to 1, 3, 4, 2, 5. Any permutation of nodes is a valid path since all nodes are connected to each other, right? So 3, 2, 1, 5, 4. Any path you take, that's a valid path on this graph, and it's a valid permutation, and your backtracking approach is going to check that. Does that make sense? Can you suggest some standard Bitmask DP questions? To be honest, if you're in TLE, then I think there'll already be questions provided to you. Otherwise, go to Leetcode and look up the Bitmask tag, right? Or on CF also the Bitmask tag. I don't know if they're exactly standard problems, but yeah, on the top of my head, I can't tell you standard problems right now. Maybe if you put this on a comment, I'll find some good ones and I'll comment it under YouTube. Okay, Anirudh? Did you understand why it's n factorial? Because in the worst case, you're going to visit all the paths in a graph, and that goes to n factorial. I can't tell you off the top of my head standard Bitmask questions, but just you can always Google it, right? A lot of people like Bitmask DP is a common question even in OAs and stuff. So you will get a lot of questions on it. Okay, any more questions? Okay, I see not many questions today. All right, then, guys, thank you for attending the session. Do check out TLE Eliminator self-paced courses once again, right? Bitmask DP is taught in level 4. Yeah. Hope the explanations were understandable. Hope you learned something and see you next time. Bye bye.